Okay, the last thing I want to think about is why are hexadecimal numbers useful to computer scientists? So go back and think about binary first. We remember that um, obviously there are no actual zeros and ones inside of our computer, and instead the zeros and ones represent the physical state of something. That state could be the state of a wire, the shape of a radio wave, maybe whether or not there's some electrons at a certain place in the computer's transistor in the computer's memory. Um, so the zeros and ones are an abstraction of a physical state. And once we've got that abstraction, right, we're thinking of those states as zeros and ones. Now we can start to think of them in chunks, and we can think of interpret those chunks of zeros and ones as binary numbers. So at that point, we get to use those binary numbers to represent real world things like letters and other symbols like that might want to type, or colors, or pixels, or or um, anything as sounds that you might have on your computer, right? So the zeros and ones get interpreted as something real. Um, so let's go ahead and take a look now at. I took the decimal number 58,079 and I wrote it out here in binary and in hexadecimal. And you should see something, right? When we have the more symbols we have to express a number, the more compact it gets. So the computers work with binary circuitry. So it's very important that we can think about things as binary numbers rather than decimal numbers. The problem is it's cumbersome to write out binary numbers. Even numbers that are not too terribly large get very, very long in binary. And when we want to work out the math to figure out what's going on inside the computer, this is not practical. Um, so one reason is binary numbers or hexadecimal numbers are compact. Okay. Um, so not a lot to write down. But there's one more thing that's really interesting. Remember, binary is base 2, and hexadecimal is base 16, and base 16 is also a power of 2. And this lends itself to, it's like, why hexadecimal instead of some other compact system? Well, because hexadecimal is also based on a power of 2, it's very easy to convert back and forth between binary and hexadecimal. So let's take a look. All right. So if I were working out this, if I told you to take this binary number and turn it to hex, one strategy based on what we've learned so far might be, well, I'm just going to turn this into a decimal number as an intermediary step, and then go and take that decimal number and turn it to hexadecimal, because I know those two algorithms. But it turns out we don't have to do that. So this is one long binary number, and I have actually broken it up in blocks of 4 just for readability, right? But think of this as one number. And I'm going to convert it to hex. So all you have to do is, if you break it into blocks of 4, is just turn each block of 4 into its convert each block of 4 into a number, and then write its hex representation. So like this one is, let's say that's a 1, no ones, that's a 2, and that's a 4. So this is the number 6, because it's made up of a 2 and a 4. And this is made up of a 1, a 2, and an 8. So that's the number 11. This number is made up of a 2. So there's no 1, there's 2, and no 4, no 8. And this has a 1, a 2, a 4, and an 8. And I add all those up, and I get 15. All right. So I just took each of these blocks of 4 and converted it to decimal. And now, when I write it as hex, it's going to be a 6. And remember, we have a symbol for an 11. So A is 10, so that would be a B. And a 2 come down. And a 15 is the symbol F. So it's real easy to take binary and convert it to hexadecimal, all right, without thinking about how large that number actually is. And we can go the other way just as well. So if I want to do this number here, all I have to do is take each individual um, hexadecimal digit and convert it to binary. So an A is a 10. A 10 is made up of an 8 and a 2. So that's the 8's place, that's the 2's place, so it would look like that. A 5 would be 1, 0, 1. And since it's only a 3-digit number, I'm going to go ahead and pad the front with a leading 0. And then a 2, well, in decimal looks like 1, 0. And since it's not 4 bits, we'll just go ahead and pad it like that. And so the hexadecimal number, A52, that is its binary representation, right? So, once again, we need binary numbers to represent the physical state of the computer, but they're cumbersome to work with. And it turns out going to a base like 16, which is also a power of 2, makes it easy for us to take that long binary representation and turn it into something short that we could work with. All right. Thanks for listening.